anglais. Parce que je maîtrise beaucoup mieux. Okay, I'm here to talk about what we are doing at STARS with François Mon in the works of modeling and recognition of human activities using video information. So, going straight forward, what we are trying to do is we are trying to understand the semantically long-term activities. And here, in this video, in the top left, you can see already the results of our framework, where it's detecting automatically some activities as preparing a meal, sitting on the chair, all the ADLs. What's the importance of these activities, or what's the difference with action, is that they take much more time than action. So they can take minutes, hours, days, weeks. We don't know where's the limit yet. So the challenge that we have to face is mostly related with overpassing a gap, which is called the semantic gap. And this gap represents the lack of consonance between low-level information and semantic interpretation of this information. For instance, here, if you have this picture, what would you say this person is doing? Okay, he's painting blue or he's painting yellow. That's the kind of answers we need to achieve. Traditional approaches are divided in two. The bottom-up approaches, where basically the idea is to get a lot of low-level features and put them into SVMs or different type of modeling approaches. And the other ones are top-down approaches, where the human intervention is very strong, and you have to do by hand model of the activities, and you try to recognize in video those handling model activities. So both of these approaches have problems. In one hand, we have the bottom-up approaches are hard to understand because it's mostly automatic, and it's very hard to update by humans. And the top-down approaches, it's very hard to model all the world by hand. So we would try to go hybrid, and with this we mean to relax as much as we can in human intervention and just to learn what is important. That's what we try to do at the end. So having speak about what we do in the challenge, the remaining slides we will talk about the framework that we propose, the evaluation of the framework, conclusion, and what we are trying to do in the future work. The framework basically is divided in 4 stages, where the first stage is the basic one of extracting perceptual information from the video, and is here marked with 1 as the input. So the input, supposing that we have a video, we propose to do it in 2 stages. The first one is to break the video into video chunks, and the second stage is to extract from this video chunk particular perceptual information. So how we break the video? The video is based on the changes of speed of the person. So here's a little bit of the reasoning of the framework. We consider that you move very fast, or you change your acceleration. You're trying to do something and you stop doing something that you were doing before. All this in the framework of ADLs, no? Indoor physical activities. So the changes of speed are measured using the global position of the person, and using a cascade of Kalman filters until we threshold a smooth speed of the person. From there, from a chunk of video, from break to break, we extract what we call a perceptual future chunk. So here's the thing. Why we think it's important to have dynamic, sizable chunks of video is because in our experience we could reduce 15 days of video to only 8 megabytes. And when you have a system that is running all the time in long-term activities, you want this kind of behavior to reduce storage space. At the end, what is a perceptual future chunk? It's a compound of trajectories, where we have global trajectories of an object and local tracklets of pixel-based motion, yeah? Which could be the hands of a person when the object is the person. So, depending on the situation, for the global trajectory, we use 1 of 3 tracking algorithms. The first one we call general tracker, which is a standard foreground, background segmentation algorithm, where we extract the silhouette of the person, and it's the normal clustering. Here we are presenting the depth tracker, which is the already known Kinect algorithm, with all the problems that it has as well. So, I mean, both of these trackers have problems, but if we have a single person and a monocular camera, we are mostly using something developed ad hoc, which worked quite good, which is based on the optical flow motion, and here we have in green some corner points, good filter to track. We cluster them by motion and position, And here you see the fastest cluster is the one painted in red. And we say that there where most motion occurs is located the person. We need to update this algorithm frequently, and for that we use already the same position of the person, like a chicken egg situation, to avoid big illumination changes. So having said something about the global tracker, we have to take in consideration that the global tracker for detecting finer activities is not good enough. For instance, here if we want to differentiate between reading and standing through the camera perspective, it's very hard. So we need something that describes more the local motions of the body parts of the person. And for that we use we extract some optical flow of good filters tracked through a video chunk, but only the tracklets that are near the starting and ending of the trajectory of the person. Yeah? So that in that sense we can be sure that it's a local motion of the person. So we use these two types of information. So a little recap, we break the video and we extract global trajectories and local tracklets of the persons per video chunk, and we have a sequence of video chunks. Yeah? But still, this is the input. The challenge still remains how we go from there to the semantic interpretation of this information. For that, we will add here in the second stage some contextual information, and we see the contextual information as a set, or as a topology, which is actually a set of interesting regions over the scene. And mainly, these regions try to describe where a person interacts with different objects in the scene. Yeah? This way, we can have a spatial location of different activities, and if you have a new video with a new person, we can link automatically, find a relationship between the activities that we're learning in one video and the other one. Here, in this part of topology, the main reasoning of the whole approach. So, supposing that we have a person, we use particular points of these persons, which is the starting point and ending point of the global trajectory of this person, because this was where the motion changed, and in the long runs, there's where the objects are linked in the scene. That's what we find out. So we use a cascade of k-mean clustering, where we use one clustering of one person, and we accumulate several persons to have a macro model of the scene. Since we have regions and sub-regions, we do this in multiple resolutions. Actually, we use 3 resolutions, so we can describe the kitchen, and inside of the kitchen we have the sink, the oven, etc. So we have 3 resolutions at the end, and we try to find these kind of things, a coarse, a medium, and finer topologies of the scene. Here you can see in a result that, for instance, in number 4 at the top there, you have the kitchen, and here you have detected the refrigerator, the shelf, and the table inside of the kitchen, for instance. So basically, this contextual information is representing a macro model of the scene. Yeah? So now we have the macro model and have the input. The input, if we look closely, is representing a snapshot of what's going on, because it's a little video chunk, and the other thing is a macro model of the scene. But to get to the semantic interpretation, we need to do something that lives inside the semantic gap. That's what we propose. So we call these units primitive events, which are little bricks that are human understandable. And we do that by combining the topology information and a snapshot. From this combination, we extract several attributes for a primitive event, but mainly I will talk about 2 of them, which is the type and the local dynamics. Okay, the type aims at showing you which one are the movements, the global movements of a person over the scene. Yeah? It could be I'm going from position A to a position B, if these are 2 regions, or I'm going from position A and moving around and coming back to position A. Since you have different resolutions, you will have different type of movement there. But at the end, what you are doing is normalizing the possible movements over the scene. Yeah? That's interesting. So that's done with the global information of the person. And this type, since it's already, you have fixed a number of regions, you have a fixed number of types, so you can color them. And in the top video, we have 4 hours of video of one person. In the bottom is another person of 4 hours. And when we put them, like overlapping them, we find out that the same colors are representing similar activities. Yeah? Here we have colored sequences of primitive events during the 4 hours. So you can find, for instance, that persons here in red are eating, and both persons are doing the same. But this